Hi, my name is Ray Holder. I'm a PhD student at the University of the West of Scotland undertaking research on analysis of the application of virtual reality and gamification to computer science education in the School of Computing, Engineering and Physical Sciences within the immersive department. The study that I will present to you today is virtual reality versus pancake environments, a comparison of interactions on immersive and traditional screens. Over recent years, virtual reality has gained popularity, and with advancements in hardware and software, it has become affordable to a larger audience. However, to date, there has been little research to establish conventions around the implementation of this technology. In this study, we built a virtual 3D environment that is presented through two different interfaces, a virtual reality system and a flat screen. We sought to make a comparative study between the two interfaces to gain better understanding of the newer VR technology and establish some best practices of presenting a user with this form of interface. 31 participants undertook a small study, all of them creative computing undergraduates in their second or third year of study, and therefore familiar with computer-generated virtual environments. Let me introduce the application. For testing, a 3D virtual environment was built using the Unreal Engine 4 game engine. The virtual world has been kept intentionally simple visually with a minimalist environment, allowing the application to run smoothly at a high frame rate. The total size of the virtual world equates to a real-world measurement of a 5 by 5 meter room. A simple grid pattern floor is underfoot, and post-processing fog prevents the participant from seeing beyond the edge of the play space. The participants are presented with four models on plinths to interact with. The four objects are a character model, a motorcycle, a robot, and a rifle. In the desktop interface, the user interacts with the environment and models by using a keyboard and a mouse. A HUD-style user interface is presented on screen at all times, with a guide on how to move around and select and interact. The desktop user can move a model in any linear axis up, down, left, right, back and forth, and rotate it by depressing the right mouse button with the cursor over the model and moving the mouse in the corresponding direction. Movement in VR has 6 degrees of freedom, commonly referred to as 6DoF, and can be executed by physically walking around the play space or using a teleport system that is implemented by the user pressing and releasing a button on the left-hand controller. The right-hand controller has a laser pointer attached to it. A model can be picked up in VR by aiming at the model and depressing the trigger. The user can move the model freely in any axis. In VR, the UI is attached to the right controller. The study was set up in a dedicated room that was large enough for the user to move safely while in VR without the risk of tripping or bumping into other objects. It was also a private room where, while in the experience, no person other than the lead investigator and the participant would be disturbed or distracted. All the participants are creative computing undergraduates. Half of the group undertook the Pancake interface first, then the VR. The other half did the opposite. Questionnaires were undertaken before and after the experience. A virtual recording of the user's movement within the virtual world was also captured during the play sessions. Two gaming laptops were used to allow a comparable performance of both experiences. One laptop with a 15-inch screen was set up to run the flat screen experience, and another was used to drive the VR system, which was a HP Windows Mixed Reality headset with two controllers. We considered the special requirements needed for virtual reality, such as place-based dimensions, and took these unique factors into consideration when testing the VR application. Conducting the playtest in virtual reality has more elements and conditions to meet than a traditional playtest. A player's body can be put under significant strain when using wearable immersive technology. The most recognized comfort issue is motion sickness. To minimize the probability, that the players will experience simulation sickness, in the application we focused upon these three main concerns. 1. Technical performance. Today's VR succeeds according to a low delay between the player's movement in the real world and the HMD screen displaying the change in the virtual world, also known as motion to photo latency. If this is low, it will deceive the brain. Poorly optimized applications and hardware issues add to this latency and can break the illusion, with motion sickness being the result for the user. 2. Application design. Design can have a great impact regarding motion sickness. Design choices to maintain performance and frame rates to make sure they run well are important. If a participant takes the role of a passenger in a moving vehicle with text to read placed close to them, then a car sickness simulation has been created. And 3. Eye strain. Users could experience headaches, nausea, and fatigue due to the eye strain while using an HMD. To negate this, during the design process, we thought about the scale and position of objects within the virtual environment. A few other points we considered during our VR testing. We confirmed HMDs and controllers were sanitized, ensure all relevant software updates were installed, prepared the play area based on the dimensions needed for the playtest, made sure the area was safely clear of clutter or tripping hazards, checked that the HMD lenses were clean and clear, checked elements like lighting and other factors would not interfere with tracking, ensured that the VR hardware was ready for immediate use by each test subject, and kept spare batteries on hand. A varied experience level of participants with VR was expected, and some needed help getting the HMD on. With each participant, we loosened all the headset fittings and had the participant hold the lens assembly close to their face. Some had to shift the lens assembly along their face to find maximum clarity. Then we tightened all the fitting once they stated that the text in the scene was clear, and then we handed over the controllers and secured the wrist straps. Once the participants had been given all the relevant information and the VR equipment was properly fitted, they were ready to start the experience. We avoided coaching the participants through the experience. Once the playtest concluded, we assisted the participants with the removal of the VR equipment. The VR experience was fresh in the subject's mind. We debriefed them. Participants were asked a standard set of questions as per the testing plan, and we gave them a survey, seen here, to facilitate qualitative analysis. Taking the results from the questionnaire, the 31 participants filled in before and after they had completed the two experiences, we compiled the results into spreadsheets and converted the data into easy-to-read graphs. A large percentage of the participants had used virtual reality headsets prior to the study, with 64.5% of them having previous experience in a VR platform. However, as shown here, a slight majority of the participants described themselves as being beginners, with 51.6% of them classifying themselves in this category. The participants were asked 3 questions regarding their thoughts on both experiences immediately after undertaking the playtest. Question 1. What did you like most about the system? Question 2. What did you dislike, if anything, about the other system? And question 3. What suggestions or ideas do you have for improving the system, whether it be desktop or VR? Using virtual estimation software built into Unreal Engine 4, we recorded the movement of the participants. This allowed playback of their head and hand movements within a virtual space, as well as the interactions with the models, as you can see here. Looking at the average time the participants spent in each of the 2 experiences, virtual reality users spent nearly 10% longer in VR, an average of 3 minutes and 10 seconds, than they did in the flat screen, which was an average of 2 minutes 9 seconds. We find all the participants picked up all 4 models when in VR. The trend wasn't carried through to the desktop version of the experience. The participants in VR also had more further interactions with the models where they took a closer look at a model within the virtual reality experience. This could have been the participant leaning in to look closer at a model by physically moving in the VR room scale space or bringing the model closer to their face by picking it up. In the desktop environment, this would have been done by zooming in on the model and wasn't undertaken by as many of the participants. The navigation method of moving around in the VR experience was considered easy by the majority of the users. This was a similar level of ease they found with the desktop, therefore showing that even though most of the users were unfamiliar with VR movement, they did not have much difficulty adapting to it. Given the experience of the users with the desktop system, you might expect that this would have led to a higher percentage of them thinking it provided a better experience. This was not the case. The VR system might have offered these participants a novel way to explore a virtual environment, which has been shown can have a positive effect when learning a new task. The majority found VR provided a more intuitive way to interact with the environment, although it was pointed out that some found it a less comfortable experience and it did not provide the same level of visual quality as the desktop. Teleportation was the most used movement system. This could have been influenced by being told how to use the system during the pre-brief, therefore prejudicing the movement ability before they even started the experience. Other factors could have also accounted for the majority of people using this method. Firstly, they didn't feel safe to walk around in the real world while they could only see the virtual world. And second, presumably the user isn't truly immersed. For example, the Matrix. A controller in the hand will certainly remind a user of that. However, the fact that just over a third of the participants also used the room scale movement to explore shows that even though they are aware of the teleportation system, they felt comfortable to roam as they would do in the real world. A distinct characteristic of virtual reality is the complete immersion of the user into the virtual environment. This allows a person to be transported into any conceivable world and to undertake any task without the physical or financial limitations of the real world. This study compared the influence of immersive and non immersive platforms on 31 creative computing undergraduates. It has shown that this demographic is open to the idea of using virtual reality system to explore virtual environments and use the interface discussed over a more familiar system. 80% preferred the VR interface, and while using immersive technology, the participants is more focused and spent 10% longer to undertake a task. Also, increased engagement is recorded in the virtual reality system, with both a greater number of interactions with the models, 100% of users picked up all the models in VR, and spent longer interacting with the objects, showing that a VR system can deliver a richer experience than a flat screen. Due to VR being relatively early in its development as a platform, there are many aspects that still need to be researched in order to make further conclusions. The design of the VR content has vast impact on the effectiveness of the user's experience, and we notice that elements placed in the user's initial view are looked at first. Although this is shown to happen in both user experiences, the effect is reduced in VR due to the ability of the user to look around the environment more easily and naturally with the headset. The main objective of this study was to playtest, observe, and analyze how the interaction interface influenced the user. We have found it to be essential in undertaking studies like this one to make any informed assertions on how to develop immersive platforms used in virtual reality. As hardware and software develop and improve, any such research will need to be updated to reflect these changes. However, we can say with confidence that user comfort, while in an immersive experience, is greatly important. The design of the interface that the user is put in can affect the level of comfort. This is not as much of a problem when using a traditional 2D computer screen, making it easier to develop and deploy an experience for a Pancake system. Thank you very much.